Hi, everybody. Your favorite type of lesson coming up, transformations. Whoop, whoop. This is the fourth time we have been revisiting transformations. So you should already have this table sort of memorized. Remember, vertical translations are adding and subtracting on the outside of our function. When it's horizontal, your transformation goes on the inside and it lies. Once again, vertical stretch or compression, it goes on the outside and it's just the normal number when you're multiplying. And then a horizontal stretch or compression, that's multiplication, but it's on the inside. And once again, it lies to you this way. It lies by using the reciprocal, so you have to flip that factor. And then our reflections. We have talked about this in the past as well. So reflections are when we make our function negative, either if it's on the inside with x, that's your horizontal. And remember, a reflection across the y-axis would be horizontal. And then on the outside, a reflection across the x-axis, so up and down, would be vertical, right? Up and down. So we're going to be applying these transformations again, but this time to exponential functions and some logarithmic functions. So first and foremost, we're going to start with the function family f of x is equal to 2x, or 2 to the x power. We actually did this in the past, so I'm just going to copy down the table from section 7.1. 2 to the negative first power is 1 over 2. And this would be helpful if you had two different colors, just FYI. We're going to be graphing our parent function. So negative 1 comma 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. We have our parent function here. And then I'm going to do my transformations in blue. So we actually have two different transformations going on. So this first one that I see here is a reflection. And since that reflection is with the x, that means it's horizontal. So over the y-axis. So instead of opening up as we go to the right, it's going to have to all turn around and go over the y-axis. So this point is now going to move over here, right? And then we have this point, which is right on that y-axis, as it isn't going to move, but we're going to reflect each point to the other side. That's our first step. And then overall, let's do this in a cool blue. This overall function, we still need to do our last transformation, which is a +1 on the end. And we're going to take that y-intercept and move it up one spot, which means every single one of these coordinates is going to have to move up one spot. And then this blue function, this light blue function is my final answer. So this is my g of x. Okay, so thinking about our domain and range, so we transformed by going up one and we reflected over the y-axis. Just talking about our domain and range, since we went up one, if you recall, our asymptote was usually at 0. We got really, really close to 0 but didn't touch it. But since we moved that up 1, that means that our range is now going to be starting at 1 and all the way up to infinity. Remember, we can't touch 1, even though this graph looks like it does. It's going to get infinitely close but never touch there. And then the domain, we didn't change anything about the domain. We can still plug in any x value that we want, so we could go from negative infinity to infinity. Right? This next one, if we look at our transformation, it looks like we have a transformation that's with the x, which means it's got to be horizontal. And then since it lies, a -2 is actually going to move to the right 2. So if we graph our parent function in red again, we're going to take this parent function f, and this only has one transformation on it, and we're going to take each coordinate and move it to the right 2 spots. And if you look, we still have an asymptote at 0, right? Since our asymptote is still at y is equal to 0, the range of possible y values remains what it was for our parent function. So it starts at 0, won't ever touch 0, it'll get infinitely close, but then it's going to rise up and up and up forever. And then our domain is always the same, so you don't necessarily need to write that down. Let's see here. We're going to be graphing the following functions, and we're going to find the y-intercept and the asymptote and describe how the graph is transformed from the graph of its parent function. Whoa, that's a lot of information, right? So, if we're taking a look at these equations, the very first thing I want to remind you of is, remember this number out front. If whenever we have something as y equals a times b to the x power, a is our initial value, which means it's our y-intercept. And then this b is what we call the multiplier. And what I mean by that is when we identify our y-intercept and our multiplier, we can create a table that says, hey, here's my x's, here's my y's. I already know my y-intercept is 2/3. That's my initial value, and my multiplier is 1.5. So if I multiply 2/3 times 1.5, I'm going to get 1. You can trust me on that. And then if I multiply by 1.5, I'm going to get 1.5. And if I keep multiplying by 1.5, I will continue down the table. And then here, in order to work backwards in the table, you should always have at least one negative value. Instead of using our multiplier, we're going to divide by that multiplier in order to work backwards. In this case, if you were to plug this in, so 2/3 divided by 1.5 is around 0.4. You can plug that into a calculator if you'd like. And trust me. Once again, we have this graph, and we can graph this function. We know our y-intercept is 2/3. We started around 0.4, 1, 1, 2, 1.5, 3, 2.25. You can see that this graph still has got a little curve to it, but it looks like it's not growing as fast as some of the other ones that we've graphed, like our parent function here, right? So really, this 2/3 out front is our y-intercept, right? That's our initial value, or that y-intercept. And then a transformation, well, we just have a different multiplier, right? Our y-intercept, once again, is 0, 2/3. And then our asymptote, we didn't really slide this anywhere. We didn't reflect it. So our asymptote still is y equals 0. So that's a good sign. So next up we have graph B. This question, you're able to see a little bit more of your transformations. This one was of the form y is equal to a times b to the x. We're going to do the second example in light blue just so you can differentiate. So if we ever have a negative in front of the x, that means that it's a reflection horizontally, which means over the y-axis. And then this +1 means that we have to move. It's a liar, so this is horizontal. It's with the x. It's with the exponent. So since it's a plus 1, we're actually going to have to do the opposite and move left 1. So we're going to take our original function, and every parent function should go through the point 0, 1, and it should grow as you go up to the right. You could copy this graph from 7.6, but that would take a lot of time. So, sorry, we're going to graph our parent function. I'm going to do that in dark blue. And then we're going to do our left 1 and our reflection. So I'm going to do the reflection first. I find that easier. So instead of opening up to the right, it's going to open up to the left. And then what we're going to do is take this y-intercept now and move it to the left 1. So we're still going to be opening up as we go to the left, but we're moving it to the left 1. And this red graph would be my final answer for h of x. I know this is tricky stuff. You could have made a table of values and then just ended up with a whole bunch of decimals and graphed it. But what I'm really looking for is, can you determine if this is a reflection and left 1 or not? Okay, moving on. For transforming logarithmic equations, it's a very similar concept. We don't need to talk about this table again. Vertical means with, or on the outside, horizontal is on the inside with x. But the same rules apply. So if we have something like the natural log, you can see both of these transformations are inside with x. So this negative applied to the x means a horizontal reflection, which means over the y-axis. And then this plus 2 means that we have to move the opposite direction and go left 2. Because it's horizontal, it's with the x, it's going to do opposite of what we would think. So our original parent function, I'm sure this is hard to remember, our parent function of a natural log, which was in 7.6, our parent function usually goes through the point 1, 0, and it sort of does this. So it's going to get infinitely close to the y-axis, but never get there, and it's going to sort of grow as you go up to the right, but not nearly as fast as exponential growth. So this is my parent function for the natural log of x. And what we're going to do is reflect this guy over the y-axis. So it's still going to be infinitely close to the y-axis, but it's going to grow towards the left instead of growing towards the right. And then once we have this, we can move it to the left 1 spot. And then you're going to see your asymptote needs to move with it, because we're not going to get infinitely close to 0 anymore. We're going to get infinitely close to, oh, oops. I only moved it to the left 1 spot. Let's just change this to a 1 because I messed it up. So for moving left 1 spot, our new asymptote, since this time it's vertical, it's going to be x equals, and of our transformed function h of x, which is in red, our new asymptote is going to be x is equal to -1. Okay, last little thing, we're going to do a couple examples where it says write the transformed function. It says f of x is reflected across both axes, which means I need a negative in front of the 4, and I need a negative with the x. And then it says 2 units down, which means I need a -2 on the outside. That's a vertical transformation. So my g of x is going to be equal to -4 to the negative x, and then -2. And then our last example, we have our natural log function. It says compressed horizontally by a factor of 1/2. Remember, that's a liar, which means we're actually going to have to multiply x by 2. Remember, horizontal is with the x. And then 3 units left means we're going to have to be with x, but it's a liar, so we're actually going to have to add 3. If we take our function then, we have our natural log of x, we have the natural log, but with the x, we just said we would have to multiply it by 2 and then add 3.